So we're going to calculate the frequency of an allele in a population. We do this using Weinberg principle, and that's to just easily suggest that if all of the alleles in a population are made up by one dominant and one recessive allele, then all of the alleles in the population equal 1, or 100% of your alleles. So it's very easy when something's recessive to look at the phenotypes in a population, and you can literally count them and determine what percentage of the population has the recessive trait. But what that means to us is if, for example, we look around and we count people who have a recessive trait and they are 49% of the population, then what we also know is that those that contain the dominant allele, whether that's homozygous dominant or heterozygous, are going to equal the remainder of the population. Now, so this is pretty simple so far, but how do we calculate the numbers of individuals that are heterozygous versus homozygous dominant if we can't actually see them? We can only see the phenotype that's resultant from this, being that whole 51%. So what we need to do is use the homozygous recessive to calculate the frequency of the recessive allele. So if homozygous recessive is 49%, that's 0.49 of a population, it would stand to reason that the recessive allele on its own is going to be the square root of 0.49. So the recessive allele in this case will equal 0.7. Knowing that we have the sum total of those alleles, we can now determine that the dominant allele must be the remainder. So the dominant allele, in fact, only appears in 30% of individuals. So what does this look like? If we were doing our general Punnett square, where we would calculate exactly at halfway, so for a trait that was like heterozygous crossed with heterozygous, we would tend to put them like this in our Punnett square that we learnt in year 10, and you would fill out your boxes seeing that 1/4 in exactly the area of that are homozygous dominant, 1/4 are heterozygous, another quarter are heterozygous, and the last quarter is homozygous recessive. When you apply it in this fashion, what you start to see is that in the same area of the box, if we place the dominant allele as 0.3, so 0.3 versus 0.7, if the dominant allele here is 0.3 and the recessive allele from here is 0.7 of the space along here, then the equivalent statement's true, and you would end up with an area which looks like this. So this represents the population, or the frequency of the alleles in that population. So instead of us doing these guys and just adding them up so that this will equal 25% and so on, collecting the like terms there of those two, homozygous recessive, we can actually see the effect of it on the space for the frequency of the alleles. So this area here is really represented by, in this case, 0.7 times by 0.7. So this area here is 0.49 of the whole. So it's almost half of the population that you're looking at for their phenotype as well as their genotype in that case. So here, these are the ones we couldn't determine. But now we can accurately say that the homozygous dominant are a product of 0.3 times by 0.3. So if the dominant allele equaled 0.3, then homozygous dominant must equal 0.3 squared. So this is going to equal 0.09, or 9% of the population. What you can see also from this is that the sum total of your heterozygous individuals plus your homozygous dominant individual altogether must equal our original estimation of them being 51%. So it's very simple from there to just do your subtractions. So we're looking from here. We've already got the value of RR, so we can work that out by substitution. I hope that helps you understand. how you calculate the frequency of alleles in a population.